Right then, logarithms, when do you use them in A-level physics? Tends to be nuclear physics and capacitance, but they can appear in the practical side of your papers. In nuclear physics, we can use them to derive our equation for half-life, and in capacitance, we can use it to derive the equation for the time to half. So starting off, when I'm using logs, because of the exponential nature of the equations we're using, I'm going to be using log base e, or ln. To start with, we need to look at the basic rules for logs. If you have ln a plus ln b, we can combine that to get ln ab. Ln of a minus ln of b is equal to ln of a over b, and ln of a to the power of b can be written as b ln a. So if you're comfortable with those three, we can then get into the actual physics. So in nuclear physics, we know that the number of original nuclei left is equal to the number of original nuclei at the beginning times e to the minus lambda t. Our half-life is the time it takes for that number to halve, i.e. n becomes n0 over 2. So if I sub that into my equation, I get this, and you can see there's n0 on both sides, which we can cancel. So a half is equal to e to the minus lambda t. Okay, I can now apply lns to both sides, because what that does to my power is bring it down. So ln a half is equal to minus lambda t. All right, and remember t is t a half because we're working out half-life. Rearranging for t a half, I get minus ln a half over lambda, which is true, but not in the form we want. The minus ln is like saying minus 1 times ln half, and I can bring that up to a half to the power of minus 1. Half to the power of minus 1 is just 1 over a half, which is 2. So my equation for my half-life becomes ln 2 over lambda. Okay, so being able to use logs is really useful for deriving things that you might forget in your exam. We can apply this to capacitors. Q is equal to Q0, e to the minus t over RC. My time to half is when Q is Q0 over 2, so half the initial charge. So I would have Q0 over 2 is equal to Q0 e to the minus t over RC. Cancelling my Q0s and applying a ln, I would get ln of a half is equal to minus t over RC. Multiplying across by RC, negative RC, we get minus RC ln to the half, right? Which we then use the same rule that minus ln a half is ln half to the minus 1, and half to the minus 1 is 2. So I get RC ln 2. Okay, and you might think about the time constant t, or tau, is equal to RC. What happens to my charge when one time constant has passed? Q0 e to the minus RC over RC, because I've replaced my t with RC. Well, that just gives me Q is Q0 e to minus 1, which is Q0 over e. Which is why we say after one time constant, our value has fallen to 1/8, or to roughly 37% of our initial. You may come across questions in your practical side of your course where you need to plot a straight line graph, and you might have some sort of power law that looks like this, and you might be asked to get that into form y equals mx plus c. I will be doing another video on all of the equations that you might need to manipulate into the form y equals mx plus c, but for this I'm just going to use one because it involves logs. So if you apply a log to both sides, and it can be any log, be log base 10, I'm using log base e because that's what I've been using. We can see that I have a times x to the b, so that is ln of a plus ln of x to the b. And then I can bring that b down to get b ln x. Swapping these over, I get b ln x plus ln a. That is now in the form y, so I'm on my y-axis, I'm plotting ln y. On my x-axis, I'm plotting ln x. My gradient is given by b, and my y-intercept is given by ln a. Okay, so getting comfortable with log laws makes manipulating exponential equations not too difficult and something that you could access in your exam. I hope that helps. Let me know in the comment if you want me to do anything else, and I'll see you in the next one. Cheers.